Okay, hello everyone. My talk today is on quantum gates, hardware versus software implementation, and well, let's get started. So first let's talk about just software. The ultimate goal is to run quantum algorithms like these ones here. Wait, the quantum algorithms session for peak anniversary is the next one, the session after this, the final one. But then you look at the hardware, and there's a lot of different hardware. This is from the full stack quantum computing computation hardware page. So there's a lot of hardware. And so there's all these different types of hardware, which is a challenge to write software for because the hardware is always changing and there's many different types of hardware. So what bridges them? Well, if we can first talk about computer architecture, which bridges your software and hardware on classical computers. In the 1950s, when classical computers were first starting, we had algorithms at the top of like, we hope computers can run these. And then in practice, we have these giant vacuum tubes and weak relay circuits and just really minimal assembly language. And the main constraint at the time was memory. So your first computers could only have like a few hundred kilobytes of, or a few hundred bytes and then like kilobytes of memory. Now today's classical computers have just this stack of many different layers of how your software or applications are then underlying that is software. And then you have your operating system and compiler, and then you have your computer architecture, gates, and circuits. And at the very bottom is your transistors, which are like really tiny. Like the transistors today are in classical computers are at the size where even quantum effects affect their execution. And today we have quantum computers today, which we have qubit implementations like the ones on the previous slides I just went through really quickly. And we also have algorithms. Kind of in between, we have many things, but it's not yet clear where the algorithms, how to get them to the quantum hardware efficiently. And the quantum hardware is also improving. So it's just a lot of stuff. And so I guess the main point of this slide is that how quantum tool flows look today is kind of like how classical computers looked in the 1950s, just in terms of you don't really know how the layers have not separated yet between your software and hardware. But we can see ideas of what the stuff in between hardware and software might look like. So this is a graphic from Righetti's blog that shows like this laptop here is, say, your personal laptop, and then you can remotely connect to the quantum machine interface, so some computer in the cloud, which will then, if you're on the hardware, if you want to run on quantum hardware, then it'll send to these, when it says wave, that just means classical control, which then is controlling your quantum processing unit, and then that output is fed back into your cloud and then back to the user. On the left end, it's if you have a simulator, then your quantum code will be compiled to your, and then run on the quantum virtual machine. And then the output will be sent back to the user. You might also, so most people who are working in quantum software or quantum algorithms may be familiar with quantum instruction sets. So this is if you, for example, if you've done Qiskit, you can convert all your quantum software to just to QASM, which is IBM's quantum assembly language specification. A few other ones are Cirq, Quill, and CQASM. And so the most popular are embedded quantum programming languages, which are interpreted at runtime and often run on Python. So this is an example. The ones on this slide are examples of quantum instruction sets, which are less abstract, more at the gate level, but unlike classical computers where assembly code is very close, if not precisely the hardware operations, for quantum computers, there's even deeper levels underneath that. So now we'll go below the gate level. So if you have this ZZ interaction on top, so the ZZ interaction is the most commonly used 2-qubit gate in near-term quantum algorithms, and it decomposes into a C0 and then a RZ rotation on the target, and then another C0. Or equivalently, you can use a cross-resonance gate in the middle. The cross-resonance gate is how IBM implements on its superconducting quantum computers the 2-qubit interaction by default. And so from one of their 2020 papers, how that cross-resonance gate is then broken down is that it's first a 2-qubit, well, it's a cross-resonance tone on their, so, and then pi rotation on about the x-axis on the control, and then the whole thing again. And so this is the Hamiltonian for it, or the unitary for it, with where h is the Hamiltonian. So I guess I'll start wrapping up. There's a lot of quite cool things that happen with IBM's quantum computing pipeline. This is from a talk that they gave to the interns 2 years ago, where you start with, I don't like the color. Oops. Well, we're stuck with red, I guess. So your quantum theory informs your quantum device. So this pipeline is of how they design their hardware to software stack, and how, in general, which direction the changes flow. From theory, that influences how your device is designed, and then the device influences how you design and optimize your dilution fridge, which goes around your device. And then from the dilution fridge, outside of that is the room temperature electronics. Say that those are the classical like electronics that control your pulses, for example, that ultimately program your quantum computer. And then you have software. That's the next step after that. And characterization. So you need to characterize your hardware, make sure it's doing what you expect it to do, calibrate for errors, and you also have a cloud. So this is probably, in general, the direction that changes flow. Although their actual flow chart is much more complicated. Let's see if I can do this quickly. So your applications, say like Qiskit Aqua, goes to a circuit optimizer. And then you have placement and routing. So the qubits that you have, the logical qubits, they actually have to be a physical qubit on hardware. And so this is what placement and routing happens. Not only do you have to place the qubits, but the qubits you want to do gates on might not be adjacent to each other. And then you have a pulse scheduler. So the gates are defined in terms of pulses, but then each gate might be more than one pulse. And you can optimize at the pulse level as well with Qiskit pulse. And then actually I'll go this way. Then you have your quantum system, which is like your device and controller. So this flow that I've drawn so far is mostly, the applications would be Aqua, and then everything else is probably Qiskit Terra. But then you also have a synthesizer, which, for example, if you were to decompose your unitary operations, which are larger gates, for example, multi-controlled Toffoli gates can't be run directly on hardware. You'd have to decompose it into gates that the hardware can run, so in smaller gates, and then those gates have to be run on hardware. And you might also just want to, instead of running on hardware, simulate your circuit, so that could be Qiskit Air. And you might also want to simulate the pulses as well. Or, you might want to design the chips in the system, which is a Qiskit metal. And, well, there's a lot of stuff. You might want to characterize the noise and error in your quantum system. So that would be Qiskit Ignis. So this is noise, error, characterization. And hardware verification. So there would be libraries, software libraries for all of these, but it can be quite involved. Anyway, you also have open source hardware. So in addition to Qiskit Metal, for trapped ion quantum computing, RTIC is commonly used. And other real-time hardware description languages could be like Verilog, which is standardized by IEEE. I'll probably end on this slide. So I guess an overall message of this talk is that software must adapt to hardware changes and vice versa as we're building quantum hardware. Anecdotally, about half the recent improvements have been in quantum hardware. and half the recent improvements in quantum computing had been on the software or theory side. So it kind of goes all together. This slide is from this month, so actually less than a month ago, IBM announced that they're retiring their square and bow tie topologies, and so all qubit layouts will now be the heavy hex lattice as shown on this screen. So any optimizations that were past meant for square and bow tie would now have to adapt to this new heavy hex lattice structure. An example of the opposite direction where hardware has to adapt to like changes that theory and software paradigms have ushered in is IBM in February started having the capability of dynamic quantum circuits. So you can measure a quantum circuit mid-measurement, measure a quantum circuit in the middle of it, or in the middle of it, have post-selection reset on the reset your qubit values. So that wraps up my talk. Thank you, everyone, and I'll now take questions.
Thank you, Leah. That was a really interactive talk. Thanks a lot. We have one question that asks, and I quote, why is IBM doing the heavy hex lattice? I know Google does square lattice for surface codes. Any comments on that, Leah?
I think of it over time, so I'll just point you at the blog post.
Yeah, that'll be really helpful. Thanks a lot.
The blog post on the bottom says it, but basically the square lattices, if you were to instead have things that would run on a square lattice, instead use swap operations and the like to schedule a route for heavy hex lattice instead, like hexagon, then it would just be a constant overhead, and that overhead is nothing compared to the cost of the routing and scheduling in the first place. So might as well go for this.